In November 1907, a 28-year-old patent clerk in Bern, Switzerland, was sitting at his desk reviewing an application for a small mechanical device when he had what he later called the happiest thought of his life. The thought lasted only a second, but it was enough to overturn 2 centuries of physics, redefine gravity, and eventually predict black holes, gravitational waves, and the expansion of the universe itself. The thought was this: if you fall freely from a height, say, a man falling off a building, you do not feel your own weight. To you, in that moment of fall, gravity has effectively disappeared. Einstein realized that this single intuition, properly developed, would lead to a complete reinvention of what gravity actually is. In the next 12 minutes, we walk through the actual chain of reasoning that took Einstein from this thought experiment in 1907 to the publication of General Relativity in 1915. Not the simplified, pop science version. The actual mathematical journey, the dead ends, the 8 years of struggle, and the moment when the equations finally fell into place. Einstein's happiest thought was the seed of what he would call the Equivalence Principle. The idea is deceptively simple. If you are inside a sealed box and you cannot see outside, there is no experiment you can perform that will tell you the difference between 2 situations. 1. The box is in deep space, far from any gravitational field, drifting forever. 2. The box is in free fall, plunging toward a massive object. Both situations feel exactly the same to the person inside. Objects float. Light travels in apparently straight lines. Time appears to flow normally. From a physics standpoint, local physics anyway, the 2 situations are indistinguishable. This was Einstein's fundamental insight. If gravity and acceleration are locally indistinguishable, then perhaps gravity is not a force at all. Perhaps it is something about the geometry of space and time itself. The cosmos is not a place where things are pushed and pulled by gravitational forces. It is a place where the very shape of space-time tells matter how to move. To turn this insight into mathematics, Einstein needed a tool that didn't yet exist in physics. Newtonian gravity treats space as a flat, eternal stage on which masses interact through forces transmitted instantaneously across distance. Einstein needed something different. He needed mathematics that could describe a 4-dimensional space-time that itself bends and curves in response to matter and energy. For this, he turned to his old friend from school, the mathematician Marcel Grossmann. Grossmann introduced Einstein to a branch of mathematics developed in the 19th century by Bernhard Riemann. Differential geometry, specifically the tensor calculus developed by Tullio Levi-Civita and Gregorio Ricci Curbastro at the University of Padua in the 1890s. This was math designed to describe the geometry of curved surfaces and spaces of any dimension. Einstein realized that if he could express his physics in this language, if he could write physical laws that depended only on the underlying geometry, not on any particular coordinate system, he would have a theory that automatically incorporated his equivalence principle. What followed was 8 years of mathematical struggle that Einstein later described as the most demanding intellectual labor of his life. He made false starts. In 1913, he and Grossmann published a theory called the Entwurf, the outline, that contained equations that were almost right, but not quite. The theory had a fatal flaw. It did not properly satisfy a mathematical property called general covariance, which Einstein knew on philosophical grounds had to be there. For 2 years, Einstein abandoned the strict requirement of general covariance, telling himself it was not actually necessary. Then, in the summer of 1915, he was invited to give a series of lectures in Göttingen, attended by the great mathematician David Hilbert. Hilbert, working independently with the full mathematical sophistication of the Göttingen school, began closing in on the same equations from his own direction. Einstein returned to Berlin alarmed. He realized he had been wrong to abandon general covariance. In a feverish month of work in November 1915, he tore through revision after revision. On November 4th, he published an incomplete version. On November 11th, a more refined one. On November 18th, he showed that his equations correctly predicted the precession of Mercury's perihelion, a tiny anomaly in Mercury's orbit that Newtonian gravity could not explain. On November 25th, he submitted the final, correct field equations of general relativity. The field equations of general relativity, in their compact form, fit on a single line. On the left side is a mathematical object that describes the curvature of spacetime. On the right side is a different object that describes the distribution of matter and energy. The equation says that these two are equal, that matter tells spacetime how to curve, and curved spacetime tells matter how to move. This single equation, when you do the math carefully, predicts every gravitational phenomenon we now know. The bending of light by the sun, confirmed by Eddington's 1919 eclipse expedition. The slowing of time near massive objects, observed in atomic clocks flown on aircraft. The existence of black holes, theoretically proven by Schwarzschild within months of the publication. The expansion of the universe, derivable from a 1922 solution by Alexander Friedmann. The existence of gravitational waves finally detected by LIGO in 2015, exactly 1 century after Einstein's equations were first written down. Every prediction has held. Every test has confirmed it. General relativity is, by some measures, the most thoroughly tested scientific theory in human history. But Einstein himself, brilliant as he was not infallible. He famously inserted a cosmological constant into his original equations to allow for a static universe, then abandoned it as a blunder when Hubble showed the universe is expanding. He spent the last 30 years of his life trying to unify gravity with electromagnetism, never succeeding. He never accepted quantum mechanics in its mature form, famously remarking that God does not play dice. Some of his blunders turned out to be premature insights. The cosmological constant was reintroduced in the late 1990s when astronomers discovered that the expansion of the universe is accelerating, exactly the kind of thing his original term would describe. Einstein, in a sense, was wrong about being wrong. What we learn from Einstein's story is not that genius is a single moment of inspiration, or that brilliant theories arrive complete in a flash. We learn that the deepest truths of physics are dragged out of nature through years of disciplined struggle, false starts, mathematical wrestling matches, and willingness to be embarrassed in public. Einstein's happiest thought took 8 years to mature into a working theory. The result has reshaped our understanding of the cosmos for over 100 years and counting. If you love careful, evidence-based exploration of how the deepest theories of physics were actually built, subscribe to Cosmic Edge. We follow the equations to where they get quietly profound. And we tell the human story behind them honestly.